One AI model gives you one answer, but what happens when several AI models solve the same problem, inspect each other's work, and then combine their strongest ideas into one final response? You do not just get a longer answer, you get something closer to an AI team. One model may be better at reasoning, another may write more clearly, another may notice a technical detail everyone else missed, and a final model can study all of their answers and build something better than any single response. This idea is called mixture of agents, and it could change how we build powerful AI systems without relying on one enormous model to do everything. But mixture of agents is not simply opening 5 chatbots and choosing your favorite response. There is a structure behind it. There are proposers, aggregators, multiple layers, and a surprisingly simple discovery. Language models often perform better when they can see the work of other language models. So how does this system actually work, and why would a team of smaller models sometimes outperform one much larger model? Let's unpack it. Imagine you need to write a detailed technical report. You could give the entire task to one person. That person researches the topic, checks the facts, decides the structure, writes a report, edits it, and delivers the final version. This can work, but the quality of the result depends completely on the strengths and weaknesses of that one person. Now imagine using a team instead. One person focuses on research, another looks for errors, a third builds the clearest explanation. A fourth challenges the assumptions, and an editor combines the best parts into one final report. That is the basic intuition behind mixture of agents. Instead of asking one model to produce the complete answer in one pass, the system gives the same problem to multiple AI agents. Each one independently produces a possible response. These first models are commonly called proposers. The proposer agents do not necessarily need to be the same model. You might use one model that is strong at coding, another that is good at mathematical reasoning, and another that writes clear natural language. They all receive the original prompt. But because the models have different training, architectures, prompts, and reasoning styles, they may approach the problem differently. The result is not one answer, it is a collection of candidate answers. And that is where the next agent enters, the aggregator. The aggregator receives the original question along with the responses produced by the proposer models. Its job is not simply to vote for one answer. It can compare them. It can detect agreements. It can notice contradictions. It can preserve a useful explanation from one response, a correct calculation from another, and an important warning from a third. Then it synthesizes those pieces into a new answer. So the simplest mixture of agent system looks like this: one user prompt, several proposer models, several candidate answers, and one aggregator that produces the final result. But the full idea can go further. Instead of stopping after one aggregation step, you can add another layer. In the first layer, several agents independently answer the user. In the second layer, several new agents read all of those first layer responses and create improved versions. Then a final aggregator reads the refined responses and produces the output shown to the user. This creates a layered architecture. Each layer does not start from zero. It builds on the work produced by the layer before it. The process begins to look less like several isolated chatbots and more like an organized review pipeline. Generate, compare, refine, aggregate. You can repeat that process across multiple layers, although every additional layer increases the amount of computation, cost, and waiting time. This is also where mixture of agents differs from another concept with a very similar name, mixture of experts. In a mixture of experts model, the experts are usually internal neural network components. A routing mechanism decides which internal experts should process each token. The experts are all parts of one larger trained model. Mixture of agents works at a much higher level. The agents may be complete language models. They can be hosted separately. They can come from different model families, and they collaborate by exchanging text through prompts and responses. Mixture of experts happens inside the model. Mixture of agents happens between models. One routes tokens through specialized neural components. The other routes an entire task through a team of AI systems. The names sound similar, but the architecture is fundamentally different. So why can this approach work? Because language models do not all fail in exactly the same way. Ask several models the same difficult question and you may receive several incomplete answers. But the missing part is often different in each response. One model understands the main idea but explains it poorly. Another gives a beautiful explanation but misses an edge case. Another catches the edge case but introduces an incorrect assumption. Individually, none of the answers is perfect. Together, they contain more useful information than any one response. The aggregator can use that diversity. This is important because the goal is not merely to create more outputs. The goal is to create usefully different outputs. If you run the same model 5 times with nearly identical settings, you may receive 5 answers that repeat the same mistake. But if you combine models with different strengths, the system gains multiple perspectives. This is sometimes described as model diversity. And diversity can be more valuable than simply adding more agents. Consider a programming problem. One agent might focus on whether the code works. Another might inspect security. Another might examine performance. Another might simplify the implementation. The aggregator can then produce code that is correct, secure, efficient, and understandable. Or consider a research question. One agent builds the main explanation. Another searches for counterarguments. Another checks logical consistency. Another turns the result into clear language. The final response benefits from specialization even when every agent began with the same original prompt. But specialization does not always require different models. You can also give agents different roles through their system prompts. For example, you are a software architect, focus on system design. You are a security reviewer, look for vulnerabilities. You are a skeptical critic, challenge unsupported claims. You are a technical editor, improve clarity without removing important details. The underlying model could be identical, but the role prompts encourage it to examine the task from different directions. This creates 2 common approaches. The first uses several different models. The second uses one model several times with different roles or sampling settings. Using different models generally creates more natural diversity. Using the same model can be simpler to deploy and easier to control. A practical system can also combine both. You might use 3 different proposer models, ask each one to perform a different role, and then use your strongest model as the final aggregator. But there is a catch. Mixture of agents is not free intelligence. Every proposer generates tokens. Every aggregator must read the responses from the previous layer. As the number of agents grows, the total context becomes larger. The system consumes more compute. It costs more. And even when proposer models run in parallel, the aggregator must wait until their responses are ready. So, mixture of agents usually trades efficiency for quality. A single model might answer in 2 seconds. A multi-agent pipeline might take significantly longer because it must generate several answers and then synthesize them. For simple questions, this makes little sense. You do not need 5 agents to tell you the capital of France, but for difficult tasks such as architecture decisions, complex research, code review, planning, or long-form analysis, the extra work may be justified. The architecture can also be optimized. Not every query needs the full team. A router can first classify the task. Simple requests go directly to one model. Complex requests activate several agents. Coding questions might call a coding specialist. Mathematical questions might call a reasoning specialist. High-risk questions might activate a critic and a verifier. This turns a fixed mixture of agent system into a dynamic one. The AI team changes depending on the problem. However, adding more agents does not guarantee a better answer. The aggregator can still make mistakes. It may select a confident but incorrect response. It may combine incompatible ideas. Several models may repeat the same false assumption. And when all agents depend on similar training data, apparent agreement does not necessarily mean the answer is true. 5 models repeating the same claim is not the same as 5 independent sources confirming it. This is why external tools still matter. For factual research, agents may need access to search engines, databases, documents, or trusted APIs. For coding tasks, the system should run tests. For mathematics, it may use calculators or formal verification. Mixture of agents improves collaboration between models. It does not magically turn model outputs into verified facts. There is also the problem of context pollution. Imagine the first layer produces 4 long responses. The aggregator must read all of them. Some information is useful, some is repetitive, some is wrong, some is distracting. If too much low-quality information enters the context, the aggregator can become worse rather than better. So, good mixture of agent systems need careful orchestration. The prompts should clearly explain each role. Responses may need length limits. Agents should be selected for complementary strengths. The aggregator should be told to resolve contradictions rather than blindly merge everything. And in some systems, an evaluator can inspect the final result before it is returned. This creates another possible pipeline. Proposers create candidates. An aggregator synthesizes them. A critic reviews the synthesis. And a final agent corrects the remaining problems. At that point, the system begins to resemble a miniature organization. Different agents create, review, criticize, and approve the work. That is why the phrase AI team is more than a thumbnail slogan. It describes the fundamental shift. The first generation of AI applications usually asked, which single model should we use? Mixture of agents asks a different question. Which combination of models, roles, and review stages produces the best result? The best AI system may not be one model. It may be a workflow, a fast model for initial ideas, a specialized model for technical analysis, a critic for detecting weaknesses, and a powerful aggregator for the final answer. Instead of expecting one intelligence to be perfect, the system is designed around collaboration. That does not mean every future AI application will use dozens of agents. For many tasks, one good model will remain cheaper, faster, and completely sufficient. But when the task is valuable enough, difficult enough, or risky enough, using several agents can create something more reliable than a single attempt. Mixture of agents is therefore not just about making models larger, it is about organizing intelligence differently. One model proposes, another challenges, another improves, and one final model turns their separate attempts into a single response. Not one AI doing everything, an AI team working layer by layer. And as models become faster, cheaper, and more specialized, the most capable AI systems may not be defined by the model at their center. They may be defined by how well their agents work together.